Hi, my name is Julia Silge, and I am a data scientist and software engineer at our studio. And today, in this video, we are going to use the Palmer Penguins dataset from this week's Tidy Tuesday dataset. And we are going to show how to use tidymodels to build a classification model. This is a great screencast if you are just getting started with tidymodels. We're going to show how to build a model specification using Parsnip. We'll show how to build two different kinds of models, and then how to evaluate those models using Parsnip to be able to tell which model is best.
All right, it's penguin time. Let's start analyzing this week's Tidy Tuesday dataset, which is the Palmer Penguin dataset. So this is a dataset of, as you guessed it, penguins. So this is a dataset of observations of penguins who live in Antarctica. It's called Palmer penguins because they live on the Palmer archipelago in Antarctica. And as we look here, let's check out what we know about them. We have some information about their species. And if you have checked out some of the lovely exploratory data analysis that has been going around this week, for Tidy Tuesday, you've seen that there's three species. There's Gentoo, chinstrap, and Adelie. I think that's how you pronounce it. The data was taken in this archipelago near or in Antarctica, and there's islands. There's 3 islands here. It turns out as you can see, for example, the different species are on different islands, so they tend to live separate from each other. And then we have these different measurements about the penguins. We have what size is their bill, what size is their flipper, how much do they weigh, what sex are they. So let's see what we have here. And we have a little bit of missing data. And then we have what year was this data taken. So let's check that out. There. So the data was taken over 3 different years. So this is the penguins data. The penguins data. So what we're going to do in this screencast is we are going to use the penguins data for some model. We're going to build a classification model. So one thing that can be you might try is to build a classification model for species. But if you build a classification model for species based on some of these physical traits, it turns out it is almost perfect. It's almost a perfect classifier because it turns out that's how we tell species apart. It's based on what they look like the shapes of their bills and how much they weigh and stuff. So instead of doing that, what I'm going to do is I am going to build a classifier to see can we predict whether a penguin is a male penguin or a female penguin based on the sex of the penguin, based on some of these physical characteristics. So let's start out by doing a little bit of just some real quick exploratory analysis. So let's see, what should we put on the x-axis here? Let's put the flipper length, the bill length, and let's make the color equals sex, and then let's make some points. And so we just do all of this. They'll all be together, right, like this. We can see that the female penguins are shifted to smaller flippers and bills than the males. Let's make those a little transparent, and let's filter out the penguins that we don't know the sex of. And let's also facet wrap by species here so that those get So we can see them separate. And let's see, let's also make the size of the dots the same, correspond to the body mass. Body mass, like this. And let's look at what that looks like. Here we go. All right. So we can make this a little prettier by changing the names of the axes, but this is a pretty good idea. So notice that for all three kinds of penguins, female penguins have smaller flippers, shorter bills, but there is some overlap here, right? And it also looks like in general they have smaller body masses here, but there's a pretty big difference between the size of the penguins. The Gen 2 penguins are much bigger, and it doesn't look like there's a huge difference in body mass between, well, maybe some between Adelie and Chinstrap, but the bill length is really different, right? Flipper length, a little different. So we have just these penguins that are quite different from each other in terms of their relationship here. So what we're going to try to do is we're going to try to build a model that can controlling for these differences in species and other size. Can we tell the difference between male and female penguins? So let's penguins. So let's only keep the penguins that we have a sex measurement for, and then let's get rid of year and island, because we're not going to use those things for prediction. We're only going to use these things. So this is the data that we're going to use for building a model. This is not a big data set, so we'll go into a little bit of what we learn here. So let's start building a model. This is, we're going to use tidymodels for building our model here. And this video, this screencast, is going to be a great introduction if you have not used tidymodels before. Tidymodels is which I cannot spell, there we go. Tidymodels is a framework for modeling in R. It is a set of packages. You can see all the packages that are loaded here that all work together for modeling in R. And the first step in our modeling task that we're going to do is we're going to split our data into testing and training. So we're going to use a function called initial split, which splits our data into testing and training. We're going to do stratified sampling for the split on the sex column to make sure that we have the same proportion of male and female excuse me, the same proportion of male and female penguins in both the testing and the training. So what this split does is it says so here's the total here, and then which penguins go in the training set or analysis set, and which penguins go in the assessment set or testing set. The split just keeps track of which ones go in which one, and then if we want to get the data out, we use the training function, which we can then apply to the split. And let's set that equal to penguin train like so. And then we can do the same thing for the testing. Let's call it test and use the testing function. So let's look at this. So penguin train is data frame. Remember that the split just keeps track of which observations go into which into training or testing, whereas penguin train is now a data frame. It's a tibble, a data frame, and it has 250 instead of the original 300 or so that we started with, and the test set is smaller. So the default for initial split is a 3/4, 1/4 split. Now, this is not a huge data set. So if I'm going to do things like compare a couple of models or you know, if I were to need to tune models, gosh, this is not a lot of data to try to do this on. And I certainly can't use my test set to compare models, because what the test set is for estimating performance of my final model. So what I'm going to do is I'm going to create a resampled data sets of using my training set, and that is what I will use for computing performance for the models that I'm going to train. So let's do that now. Let's set it up. I'm going to set another seed here, and I am going to create bootstrap resamples. So I'm going to create the bootstrap resamples of my training data. Let's call this Penguin Boot, like so. So bootstrap resamples are resamples with replacement. So you get to the same size data set that we started with, but we sample with replacement from what we had. So we have 250 in all of these 25 bootstrap resamples, and then what's in the analysis set in this case are all the things that didn't make it in to the bootstrap resample. So that this is how many is left over and all of these, and it's a different number because they're randomly resampled. So each one of these 250 is a different 250. So I can fit models to all of these different 250 size data sets of penguins that are each of them different, so that I can evaluate them on these data sets and use this as a way to say, how good are my models doing? Okay, so I have some data ready for me to fit on these resample data sets, and now it's time for me to make some models. I am going to make two models this time. I'm going to start with just a really basic logistic regression model. I'm going to set an engine, not an encoding, but rather an engine, and I'm going to start with just a really straightforward logistic regression model with a set engine equals GLM. If I wanted, I could even do like a Bayesian model or something, but just in the interest of making this go fast for this screencast, I'm just going to do really simple, straightforward one. Let's show you what that looks like. So this is a model specification. What I'm doing here is I'm saying, what kind of model am I going to train? What I haven't trained that model yet. I'm just setting up the kind of model that I'm going to train in a little bit. And I could do something. I could do regularized regression by setting my engine to GLMnet or GLIMnet, however you prefer to say that, and I could set I could make it a lasso model like this or something. But so these are flexible functions that can be used to set up many different kinds of models that you need. So we've got one model ready, a logistic regression model. Let's also set up a random forest model. Random forests are nice because they're really they perform well with their defaults. So I'm not gonna worry about like tuning the hyperparameters. I'm just gonna use the defaults here. Random forest can be used either for classification, like what we're doing now, where we're predicting sex, or for regression. So I have to set the mode here. The mode. I'm gonna say the mode is classification, and then I also have to set the engine, because this mode here could have been Spark, like this. Like I could run this not even with R. I could, wait, did I do that wrong? Is it Sparkly R? Whoops, no, it is Spark. Spark. I could run it with Spark. I could run it with random forest like this. But I'm going to run it with the Ranger. The Ranger engine. So this is going to be my random forest specification. So I have two models that I'm going to try out here on predicting sex for my penguins. So So I've got data and I've got model specifications. Now it's time to get this ready to go together. I think my favorite way to train models with tidymodels is to use something called a workflow. And a workflow is a way to put pieces of models together like Lego blocks, where they just like fit together and you can carry them around easier in your code. And so a workflow, what it needs is a preprocessor and a model. So here are the models that we're going to use up here, but they each need a preprocessor still. So let's add the preprocessor. For us, it's going to be, let's just use a formula. And let's say the formula for the preprocessor is going to be, we're going to predict sex, male versus female, with all of the predictors. So let's remind ourselves what is in the data. So we're going to predict this column, sex, with everything else. Species, all these things here. I think this could be interesting because random forest is a tree-based model, and it is able to learn learn interactions. So for example, if the different species of penguins, if four different species of penguins different from relationships between the physical characteristics are important, the random forest model will be able to learn that. On the other hand, this is just a straight up linear model, just a very simple linear model. And so by doing both of these models, we're kind of setting them up to be able to compare them and see how they'll work here. So let's call this the penguin workflow, and let's see what that looks like. Notice what we have here. We have for a preprocessor the formula, which is this thing, the outcome, sex, predicted by everything else, and we don't have a model yet. I didn't add a model here because I'm going to actually do it 2 times. So I'm going to reuse this workflow and add different models to it. Let's do that. So let's take the penguin workflow and let's add a model. Let's start with the logistic regression model. And then it's time to fit it. So I could just plain fit it to the training data like this. Data equals penguin train like this. Just fit it one time. Look, I've just fit a logistic regression model. But I don't want to do that. I don't want to fit it one time to the training data. Instead, what I want to do is I want to fit it to those resamples. And I am going to, so I'm going to fit it to the resamples, penguin boot. The reason I want to fit it to resamples is because I want to be able to compare the logistic regression model and the random forest model. And I want to be able to have a more robust estimate of performance. I want to be able to compute performance metrics for these 2 models. Let's add a control resamples, and let's save the predictions here, and let's make verbose equals true so I can watch this as it goes by. Let's call this GLM results like this. So let's train this. Hopefully you can see this. The bootstraps are going by. Remember, there's 25, so we'll watch it go. It's looking at the model and then doing predictions and so forth. And let's show you what it looks like. So now it looks pretty similar, right, to the resampling that we had before, the bootstrap resampling, and now we have the results. So the splits, that's what we had before, but now we have other things. We have metrics, notes, which hopefully are empty, no notes, and then predictions is what we have. So let's do the same thing. I'll just copy, and let's put RF spec here and RF RS. So now this is the random forest results. So this one is running ever so slightly slower because this random forest is a little more computationally intensive, but it's very small data, so it still doesn't take very long. So we did it. We trained 2 models. This data is pretty small, so it does not take long to do. All right, it's time for us to evaluate how these models did. Okay, let's start with that collect metrics is this function that will go to results like this and get out the metrics. So let's start with that random forest results. Okay, not bad, not bad. So based on the data that we have in the Palmer penguins data set, we can predict male versus female penguins with pretty good accuracy and the area under the curve for an ROC curve is quite high as well. So this is pretty good. So this is for the random forest model, which is, remember, the tree-based model that we would expect to be able to learn interactions. And now let's do it for the linear model. Well, would you look at that? So the linear model actually did slightly better. Is that right? Yes, that's right. So the linear model, I mean, if you look at these errors, see, 1, 2. Oh, I mean, these are basically the same, but I mean, I guess it does slightly better. It does slightly better. Okay, so very like this. Let's see, 1, 2, 3. I'm doing math in my head, which I'm very good at. Okay, so these are very close together, perhaps the same. But if you told me that the linear model and the random forest model did the same, and then what do you want to do going forward? I would say I picked the linear model because, of course, linear models are easy to interpret, fast to implement, easy to easy to deploy, et cetera. So let's move forward now with that linear model. So that's kind of interesting, actually. The linear model, just straight the linear model, like no interaction, no difference, species by species difference between the relationships in the physical characteristics did just as well as the random forest model. It's possible with more data we would be able to tease out something different, but with the amount of data we have, that's what we have, that's what we get. So let us we saved the predictions. Remember, we have those predictions there, so we can start to understand a little bit more deeply how some things about those predictions that we made. For example, we can look at a confusion matrix. These are resampled, so let's use a resampled confusion matrix like this. So this is like in a tidy form of a confusion matrix. So these are correct predictions, and these are incorrect predictions. So it looks like we're doing about the same for male and female predictions. We don't have like a huge problem predicting one class versus the other class. So that is good to see. Let's make one of our metrics here was area under the curve for an ROC curve. So let's actually make some of those curves. We can use a function called collect predictions, which is similar to this collect metrics function in that it goes to an output like this and goes to one of these columns and gets it all out. So let's get that all out. So here are the predictions. So this sex column is the real column, the real sex of the penguin. This is the predicted class, and then these are the predicted probabilities for each class, like so. So let us compute ROC curves. So we're going to group by this ID so that we get 25 different ROC curves. So group by ID, and then we're going to use the ROC curve function. So the first thing we have to say is sex, and then the prediction or the predicted probability of being the baseline class, which is, I think, female. I think this is right. I think it'll come out upside down if I didn't do it right. All right, and then we can start making a, well, we can just do an auto plot. If we want to make a prettier plot, we can do it ourselves. So here's an auto plot version of this here. So notice, so let's take so what's going on here? So if you've been around machine learning and modeling a bit, you have seen plots like this, I bet. But you know what? I feel like making this prettier. Okay, so you probably know what goes on this. So 1 minus specificity goes on the x-axis. Sensitivity goes on the y-axis. Let's make color equals ID. So we're going to put that that dashed line, this dashed line of slope equals 1 tells us what would happen if the model was just guessing randomly. So the farther away that our lines are up in that corner away from this dashed line, the better our model is doing. Then we're going to use this geom path, and we don't need that legend here. It doesn't really matter to us which of those lines is which. And let's make those lines a little bit transparent and a little bit thicker. And then if you want to make your plot not rectangular but square, you can make it like this. Nice. Prettier. I'm happier. Okay, so these notice that they're pretty jaggedy. That's because of how little data we have. And notice that they are all up in this corner here because you saw what our when we computed our ROC AUC, it was quite high. So that's why it's all up in there. So this gives us an understanding of what the variation is from resample to resample of how different our ROC AUC is from resample to resample. So this is good to be able to see and understand. Okay, so we've been exploring what our results are on these what our performance is as computed on these resample data sets, but it is finally time to come back to the testing data. Notice that we have not touched the testing data this whole time because the testing data is a precious resource that can only be used one time to estimate performance on new data. That's the purpose of the testing data. So what we're going to do is we're going to use the last fit function. So what the last fit function does is it fits the final best model to the training set and evaluates on the test set. So our best model is this one, this logistic regression model. So let's take the Penguin workflow. Let's add the model again. Where'd it go? This model, the logistic regression model. And then we are going to do last fit. What do we fit on this time? We fit on the what it takes here is the split, because it needs to know both the training data and the testing data. So it takes the Penguin split. So it's going to train on it's going to fit on the training data and evaluate on the testing data. So let's call this Penguin final, like so. So we're training again, one more time. But whereas before we trained one time, we trained a bunch of times on the resamples, now we trained one time on the training data. So we can now collect metrics on this object. So what we have here, these metrics are computed on the testing data. These are metrics on the testing data. We can see we're doing about the same as we had before. We don't see big changes, which is good. There, that is what we want to see. And let's look at the predictions here, so penguin final. So here are the predictions for, remember this is how big our test set is. And we have for each of the real sex of these penguins, what is their predicted sex? You can see this first one, it got right, the second one it got wrong, and so on down here. So we can do a confusion matrix here for, let's say, sex, the truth, and then the predicted class, like so. So, you know, these are the ones that are correct, and these are the ones that are incorrect. So this, the confusion matrix helps us understand how our model is doing for the two classes. And as we wrap up and start to do just a few last things, another thing we can do is we can actually get the fitted workflow out. So that's right here. So let's just get that out with like $, like that. So this is a fitted workflow. It has a preprocessor and a model, and it is not an unfitted workflow, but actually a fitted one. Notice that it has coefficients here that have all been, we know what they all are. We can tidy this like so, and we get these estimates out. Not only can we tidy it, but we can tidy it with exponentiate equals true like this. So these are the coefficients, and now these coefficients are now exponentiated, which means now they're odds ratios. So now that they're odds ratios, let's arrange them so we can see them from, I guess it doesn't really matter, but we can see them from here, they're small to big. So let's look at this biggest one here. So the biggest one here is almost 4. So what does that mean? So for every 1 millimeter increase in build depth, every 1 millimeter increase in build depth for a penguin corresponds to a almost 4 times higher odds of being male. So the build depth is very important for penguins being male. Who knew? Not me. Look, flipper length, the p-value is quite big. So that one's not so important for sex. These estimates here are probably about like how many male and female of these species were in the data set. And this is measured in grams. We maybe should have changed it to kilograms, I guess, if we wanted to. But for every 1 gram increase, there is in body mass, there is a 1% increase in the odds of a penguin being male. So that is how these odds ratios work. So this is interesting because I think that first plot I made way up here, let's copy it and put it down here, I think had flipper length on the x-axis. Let's look at it again. Yeah, so flipper length is on the x-axis, but if you notice, these are pretty overlapped, especially here. So what if instead of flipper length, let's put the other bill one, bill depth, which is the one that apparently is super different. And it does separate them out much more dramatically. Bill depth and bill length does separate the male and female penguins much more dramatically than flipper length, for example. So bills must be really, really important for penguin sex, which I didn't know. So that's pretty cool.
All right. We built one logistic regression model and one random forest model, and we evaluated their performance using resampling. We found they performed basically exactly the same, and so then we used the logistic regression model, the linear model, to move forward, and we looked at the coefficients and understood which of the predictors were most important for distinguishing between male and female penguins. So I hope this was helpful, and thank you so much for watching, and I will see you next time.